Derivatives. We want a way to summarize how a function changes as its argument changes. One such measure is the slope. However, we generally use an alternative measure, the derivative, which is essentially the slope at a particular point. We illustrate the distinction between these two measures using a function of a single variable, f colon. Real numbers, all real numbers are an element of all real numbers. The usual definition of a slope is rise over run. That is the change in the value of a function when moving from point x sub 1 to another point x sub 2. Slope equals rise over run, which equals f of x sub 2 minus f of x sub 1 over x sub 2 minus x sub 1. This definition of a slope depends on comparing the function at two different points, x sub 1 and x sub 2. However, typically we want the slope of f at a point. To determine the slope at a point, we first implicitly define the difference, h. Between these points as x sub 2 equals x sub 1 plus h, substituting this expression into our formula for the slope gives us f of x sub 2 minus f of x sub 1 over x sub 2 minus x sub 1 equals f of x sub 1 plus h minus f plus x sub 1 over h. The derivative of a real value function f colon the set of all real numbers yields the set of all real numbers at a point x in all real numbers is the derivative of f of x with respect to x equals the limit as h approaches 0 of f of x plus h minus f of x over h, which is equation capital A dot 2. In the text of this book, we use two different notational conventions to denote the derivative of a function. Here, and in most places in the text, we write the derivative using the notation df of x over dx. Sometimes, for notational simplicity, we omit explicit reference to the argument of f, writing the derivative of f at x at df over dx, where no ambiguity results. The derivative has a graphical interpretation. The derivative has a graphical interpretation. The slope of a function between 2 points is equal to the slope of a straight line connecting those 2 points. The slope of such a straight line can be computed using the rise over run formula in figure capital A dot 2. The slope of a function between x sub 1 and x sub 2 is equal to the slope of a straight line connecting the 2 points b equals open parentheses x sub 1 and f of x sub 1, close parentheses, and x sub 2 and f of x sub 2. Now fix one of the points B and move the other point ever closer so that the run h equals x sub 2 minus x sub 1 gets smaller and smaller. If the derivative exists, the rise f of x sub 2 minus f of x sub 1 equals f of x sub 1 plus h minus f of x sub 1 will eventually get smaller and smaller as well, but typically at a different rate than the run. The limiting value of the ratio of the rise to the run will be the slope of an infinitesimally short line, the slope of the function at a point. The limiting value of this slope is the derivative, which equals the slope of a line tangent to the function at b.